Oops. I'm talking to myself and I'm muted. Ha ha ha. Let me try this all over again. Hi everybody, welcome back to Chem 161. Today we are going to resume discussion of Chapter 1 topics. I don't know if we will actually finish Chapter 1 today, but we will definitely make a big chunk out of it. Let me see here real quick. Oh my goodness. This is what I'm dealing with all morning. Maya, please. No, you don't get to stand in the hallway and meow at me. She's trying to hide around the corner, and I'm trying to spray her with water. It's not working. Oops, I didn't actually hit this button here. There we go. There, now you can actually see stuff. That's useful. Alright, today we are going to start with a discussion of matter, what it is, how we can categorize it and classify it. And, oh my goodness, my cat came right back. Maya, go away. She's been a pest all morning. Cats. Alright. In chemistry, we are going to be studying matter and how it interacts with other types of matter. Now, we're going to be interested in what phase is present, what type of matter is present, what elements are present, so on and so forth. So, first thing we need to do, obviously, is define matter. Matter is anything that contains mass and occupies space. It has to have both of these properties. Now, for solids and liquids, obviously that's stuff contained in a space. Gases are a lot harder to conceptualize because many gases are transparent. For instance, the air that you are breathing or looking through that surrounds us all in like our room, on the outside of our homes, and extends all the way up to the edge of the atmosphere. That air is optically transparent. You can see right through it. But there is matter there. There are atoms that are moving around. There's a lot of atoms, actually. And they are colliding very, very quickly with each other and all of their surroundings. And we'll discuss the effects of that when we talk about gases in 162. But gases are considered matter. There is stuff there. You can determine its mass. It's not difficult to do. You just need to employ a vacuum. We're going to look at the three phases of matter in this class that are common. We're not going to look at things like plasma or Bose-Einstein condensate or supercritical fluids. Like those are things that exist but aren't in a normal realm of accessibility that we would actually see them used in. Solids, liquids, and gases, however, are all around us. They exist at room temperature for different elements and substances. So we're going to focus primarily on those three phases, although it is important to recognize that other phases do exist. There are more than just three. I just briefly mentioned what a plasma is here. Plasmas are ionized gases, so the sun is a plasma, fire is a plasma, lightning is a plasma. Plasmas tend to emit light, they tend to be really hot, and they tend to be really neat to look at, and that's kind of all we care about. We're going to stick to the solid, liquid, and gas. Now, what do those phases look like at the molecular level? I guess that's on my next slide here. Do I not have that on here? I guess I don't. Okay. I'll just draw a picture of it in a second here. Excuse me. When we look at each of the phases, in terms of its shape and its volume, we can observe different properties. For instance, if I have a solid, like this one right here, my solid's going to have this rigid shape that isn't going to change if I slosh it around the container. So you can imagine picking up this flask with the solid in it and kind of whirling it around so that you like mix its contents, and that solid will just kind of bounce around. It'll still be a cube after we're done mixing it. So the term that we use for its shape is that we say its shape is fixed. Now, I'm assuming that we're not deforming the solid in some way. Most solids are resistant to deformation. Now, if the shape of something is fixed, then its volume must also be fixed too. And that gives us something that we can use to compare other substances against. So if I can find something that is not a fixed shape but does have a fixed volume, it would not be a solid. And it turns out that that's how a liquid functions. Liquids have variable volumes. Or I'm sorry, variable shapes. They have fixed volumes. What that means is that if this right here is the 10 milliliter line, I could find another flask that has a different gradation on it, and then this would be the shape of the liquid in there, but its volume would still be 10 milliliters. As you can see, these two shapes are not the same, but their volumes are the same. Liquids occupy the volume of their container, and the shape of their container as well. I misspoke there, sorry. Liquids have the shape of their container, but they have whatever volume they go up to. So this would be the volume of the container up here, but liquids can't fill that. They won't expand to fill their container. For the last phase, the gases expand to completely fill their container in its entirety. So a gas has a variable shape because it's the shape of the container, and also a variable volume, again, the shape of the container. So if my container is sealed, then the volume of the gas is just the shape of the inside of the container. If I were to remove this cap, then the volume of the gas would then be everything else outside the container, because it would escape and then fill the atmosphere. And it would just diffuse over the entire atmosphere because that's its new container. If I compress the gas by, say, pushing the stopper in further, then the compressed volume is now the new volume of the gas. Now, what do these substances look like at the atomic level? Let's take a little bit of a look here. That disappeared, so let's put this back on the screen. There we go. Let me try and line this up so that it's under what you're going to see here. All right, so for a solid, solids tend to be very regular and ordered structures with no molecular movement. I'm a little bit too far to the right here. There we go. So there is very little to no motion. And in fact, the molecules or the atoms just kind of tend to be there and vibrate. So the atoms will wiggle in a solid, or the molecules will wiggle in a solid, but they won't move. When they begin to move, that's when you get into the liquid phase. And so liquids are actually very highly disordered. And the liquid molecules are all moving in whatever direction they can. Sometimes they bounce off each other. In fact, a lot of the time they bounce off of each other. But they're all moving. They're all moving around each other, but they're not really moving away from each other. They are still quite close to each other. So liquid molecules have lots of motion. And they are in close proximity to one another. Now, if my molecules start moving faster and faster and faster, they start to get further and further and further apart. On average. And when that happens, that's when we enter the gas phase. I don't know why I'm tempted to just write wow at the bottom of this, like it's a Doge meme or something, but in a gas, molecules move extremely quickly, but the density is very, 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 very low. And they end up being very, very far apart from each other because they're just moving so fast. It'd be kind of like if all the particles in the liquid just sort of took off outside in outside directions at once. And then they would become a gas. And in fact, that is something that will happen. That's how boiling occurs. The molecules that are on the surface of the liquid have such high velocity that they escape and they become a liquid, or they become a gas. Generally speaking, if you add heat, you will change state from solid to liquid to gas because molecular motion is more or less what governs this. When you have very little molecular motion, you have a solid. When you have a lot of molecular motion, you have a gas. And if you have somewhere in between, you have a liquid. There are other ways to change phases, such as modifying pressure, but we'll discuss pressure in a little bit more detail once we get to unit... I don't know what unit the gas chapter is. I want to say 8. But it's in 162. So we will get there when we go to the next class. All right, so on this slide, I have some important distinctions for terminology that we're going to use in this class. When you determine the amount of stuff that is in an object, such as this astronaut here, you are determining the mass of that object. Now, if you put something on a balance, you can determine its mass, but the term that is used to do that, colloquially, is called weighing. And this is problematic because the term weight and mass are not the same. So these are not equivalent. Mass is just how much matter something has, whereas weight is how much matter something has multiplied by the acceleration of gravity. In other words, something's weight depends on gravity. If you go to the moon, your weight goes down because the moon has a lower gravitational field. However, your mass remains constant. You can see that in this diagram up here. We have the space astronaut in a spacesuit weighing himself on Earth, and even with all of his equipment and kit, he weighs less than me, which is just like a little bit demoralizing, but that's okay. So on Earth, he has a mass of 100 kilograms, and his weight, which is a force, is 980 newtons. But when we go to the moon, he still has a mass of 100 kilograms because he has the same amount of stuff in him. Same number of atoms and such. But his weight is reduced because the force of gravity on the moon is lower. By a factor of like 8 or so. Best weight loss plan ever. Go to the moon. You'll feel so much better about yourself. I lived a miserable life where I weighed 260 pounds. Then I went to the moon. Now I only weigh 120. I feel fabulous. That was me. That's my pitch. Now, why do we use the term weighing instead of massing? I don't know. It is just sort of colloquialism or convention, I guess, that we have adopted. So be very mindful of this term right here. It will be used just like, oh, you need to go get the weight of something. Please go do that. And what we always intend in chemistry is its mass. I can't think of an instance where I would want to know the weight of a compound because we don't care about gravity in chemistry because we assume that gravity is going to be constant. In physics, gravity is pretty important because it governs all sorts of different interesting relationships. But in chemistry, we just don't care about it because it doesn't affect our results appreciably. Now, when you do a reaction with matter bumping up into other matter and then possibly transforming or not, all that's really happening is you're rearranging the states of the matter at the atomic level. And by states, what I mean is like arrangement of electrons, Not necessarily physical state. So it may become a gas, or it may stay a solid, or something like that. It may become more soluble, things like that. All of the properties end up changing based on the new configuration. But what does not change is the amount of matter that's there. And so this is called the law of conservation of mass. When you do a reaction, the amount of stuff that is in the container before and after the reaction remains constant. Now, a great example of this is when beer is made in the brewing process. So right here, we've sealed the container. Nothing can get in or out of the beer. And so when we mix the beer together, we put in the yeast and the sugar and the flavoring ingredients and stuff like that in the pre-beer. I don't know the term pre-beer. I don't actually brew beer. I have friends that have done it, and it turns out okay. Like, I like beer, but I've never really had great, like, home brewed beer, to be honest. Anyway, when the container is sealed and the reaction begins, what ends up happening is the fermentation process, where bacteria reacts with sugar, and you make ethanol and carbon dioxide. You also make other products, but the big ones are ethanol and CO2. Ethanol is what we drink the beer for, and then CO2 gives it a nice bubbly acidity to it, which is desirable for beverages. I say that because I'm drinking something carbonated right now, my seltzer water. It's called the wort. That I may have heard. That sounds familiar. I may have heard friends say that word, or maybe I'm thinking of something similar in like some sort of like home, like cider or like mead, or I don't know. I just drink the stuff. I don't make it. But anyway, since the container is sealed, nothing can really escape outside of the container. And so the mass of what's in here at the start of the reaction must be the mass of what's there at the end, because all the matter that's in the bottle is still there. When you open the bottle, the carbon dioxide would escape and its mass would change. It would actually go down. This is true of every experiment. In fact, in Chapter 2, what we're going to learn is that many scientists tried a bunch of different experiments to disprove this theory, and what they found was that if they just did reactions in sealed containers, like a glass sphere or something like that, and weighed before and after, there was no change at all, no matter what reaction they did. And so that's how we ended up with this law. It's a law because it explains how matter behaves, like the mass doesn't change. Now, why is this the case? Well, we don't really have a good explanation for why does the matter not change, or the mass not change. That would require us to go into a more complex discussion of what matter is in terms of like stuff in the universe and spatial, like its volume, stuff like that. Like it's beyond the scope of what I can really describe, because we're getting into complex philosophical physics at that point. Now, the conservation of mass is actually really useful because we can use it for various applications. Because we can always assume that it will work. For instance, if I take Alka-Seltzer, and Alka-Seltzer is a surprisingly complicated reaction. Alka-Seltzer is sodium bicarbonate and citric acid pressed into a tablet, and when you put it in the water dissolves it and allows the two parts to contact each other, which then react very vigorously. You get sodium citrate, carbon dioxide, and water as a result. Now, the sodium citrate stays down here. And so does the H2O, and it just sort of floats around in the solution. But the carbon dioxide will bubble out of the cup and escape. And so you can actually do an experiment where you put a cup of water and a piece of Alka-Seltzer on a balance, and you get their mass, and then you put the Alka-Seltzer in the water, and you can watch the mass just go down as the carbon dioxide escapes. And so Let's suppose that we did this experiment where I added a 10-gram tablet of Alka-Seltzer to 50 grams of water, and after all the bubbling was done, the mass of the solution was determined to be 57.9 grams. Well, according to the conservation of mass, all the mass needs to be accounted for. So how much carbon dioxide must have been produced in the reaction? Well, we can say I had 50 grams water plus 10 grams Alka-Seltzer. And then afterward, I had 57.9 grams of these plus whatever this must be. That should be a 7. It looks kind of like a 2. Where's my cursor? There it is. And so you can do the subtraction, and you should get 2.1. In the laboratory, what you can do is you can weigh your products and you can weigh your reactants. And if you get something very different on both sides of the equation, then you know that your system that you were reacting with either emitted a gas and the gas escaped, maybe it absorbed a gas and matter went into the system. That would tell you that oxygen is being involved, or nitrogen, or some other gas in the atmosphere. Or it would tell you, oh, I had a leak in my system, or I lost something, or an error somehow has occurred. So using the mass balance can be actually very useful as just sort of a quick glance at your reaction to try and learn something about it. All right, so we talked enough about generic matter. Let's talk about more specific matter in terms of what we're going to be studying, which is elements and their properties on the periodic table. So I'm going to give you a sample of copper for this example. Boop, there it is. And then I'm going to ask you to cut it in half. And so you could do that pretty easily. Boop. And then I'm going to ask you to do it again. Boop. And then again. Boop, 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 boop. And you're going to do that over and over and over and over and over again 70 trillion times. Eventually, what you get to is the smallest possible piece that resembles the original material that we started with. That smallest piece is called an atom. Now, if you cut the atom in half, what you get is something completely different. So there is a limit to the amount of subdivision that you can do for a sample of copper. Or a sample of anything, really. So if I gave you nickel or cobalt or iron or what have you, eventually, after cutting it in half over and over and over again, you would end up with one single piece that is that element. And if you cut that in half, you get other things. We'll call it other things for now, because we'll talk about nuclear chemistry very briefly in Chapter 2. Now, atoms are interesting because they're going to be the focus of chemistry. We're going to look at individual atoms and what they are capable of doing, and then extrapolate that to macrosystems where I put in like a giant chunk, and by giant chunk I mean like maybe 10 grams of, say, copper, and because I know all the copper atoms inside that chunk are all identical, they'll all behave as if they were at the atomic level. Are they the isotopes? They are partially isotopes, but what's actually happening is if I were to cut this copper atom in half, like that, I would get two halves of this atom that would be different elements. And we will talk about that briefly when we get to isotopes. But for something like copper, I'm trying to find it on the periodic table, you get, like, as a result, you get silicon and phosphorus, because their atomic numbers add up to the one of copper. And that's nuclear chemistry, which we're going to talk about when we get to isotopic notation and Chapter 2 with mass spec and things like that. How big are atoms? Atoms are extremely tiny. On the right, I don't know where I found this picture. Oh, it says right there. It must be the textbook. But the microscope that is used there is called a scanning tunneling microscope, which uses electrons and electron diffraction. And each of those little circles that you see there is a gold atom. So I'm trying to circle a few of them just as an example. Each of those is a gold atom. Now, due to constructive and destructive interference, some parts of the image are in higher resolution than others. So you get this weird sort of like linear pattern with the lines, and that's just due to how light works. And in this case, specifically electrons, because we're using electrons in the microscope. On the left is just gold. You can tell the difference between gold and fool's gold by the fact that gold is very lumpy. And there are few smooth surfaces. And the reason for this is because gold crystallizes in sort of a random way. The atoms are just sort of stuck to each other in random haphazard directions. So your ore tends to look very like wispy and spiky and flaky is probably a good word for it. Whereas fool's gold is an ionic compound, and it looks the same color as gold, but it's very, very cubic. It has very flat surfaces. These are just fun facts. I'm not going to test you on the difference between gold and fool's gold, but people like fun facts more than they like facts that I will test them on, I guess. So now, as far as individual atoms are concerned, when I draw a solid like this, so if this is like, say, my gold medal here, we'll go like this. So we'll call this gold medal. Each of these individual atoms of gold exists, and it just wiggles in place. We call metals atomic in terms of the atoms all exist independently, even though they are bound together by metallic bonding. But to describe matter in the atomic state is pretty rare. It's very rare to see individual atoms of something floating around. It turns out that only really noble gases do this, at least at room temperature. Most matter exists as combinations of different elements bonded together through shared electrons. So, for example, this would be water. So here's oxygen, hydrogen, and hydrogen. If you have atoms that are stuck to each other through bonds, we call those molecules. Now, the differentiation between the metal up here, so this is a metal, and this is a molecule over here, is that my molecules have discrete units that don't just connect to an infinite number of neighbors. So in my metal, all of these atoms are bonded to each other, and so this just goes on forever until you hit the edge of the metal. But in a molecule for water, my O is connected to two H's and that's it. The H's are not connected to other O's or other H's or anything like that. So molecules are these discrete independent units that exist. And here's some examples of those right here. Now, whether the atoms are identical or whether the atoms are different, it doesn't really matter. A molecule is just an independent entity of a collection of atoms that are bonded together. Oftentimes we'll represent different atoms with different colors. These colors that are shown are very common, so hydrogen is very often represented as white, oxygen is red. Phosphorus and sulfur are a little less common. Sulfur is usually yellow. I've seen phosphorus be both purple and orange. Carbon is the other big one. Carbon is pretty much universally black. And oftentimes these colors are selected based on things that contain this atom and the color that those things are. For example, carbon is the primary atom involved in charcoal. In fact, charcoal is entirely carbon. And charcoal is very black. So we just use carbon atoms as the same color. Oxygen is what's involved in fire, and fire is often depicted as red. It's also the color of blood, which blood turns red once it's oxygenated. So oxygen is just assigned red. Sulfur by default is yellow when you find it in nature. Sulfur, clumps of sulfur are just yellow. Things that contain sulfur in them tend to be yellow, and so on and so forth. Molecules can get pretty big and complex, and there's really no upper limit to how big a molecule can be. The limit is your imagination. Or, practical physics, so. Alright. On the left is a glass of water. That made me thirsty, so I had to drink some water here. On the right is cake. Now, we could define each of these in terms of the substances that make them up. So I could say, oh, they all contain atoms, so there are definitely atoms of hydrogen and oxygen in the water. There are definitely atoms in the cake. Carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, all sorts of different atoms in there. They make different molecules, so there would be sugar molecules. There's probably caffeine molecules because it's chocolate. There are definitely lipids because there is fat. Things like that. We can assign all sorts of different categories and classifications to these two samples of matter that are on the screen. But what I want to do for this experiment is I want to try and differentiate between pure matter and mixed matter. And so the question that we ask for this is, which of these is pure if purity by definition means there is only one thing and it's not diluted by a number of other things? Well, if you know where you can get pure cake, let me know, because I would be very excited to find this out. But cake has multiple things in it, right? There's frosting, there's the cherries, there's chocolate, there's butter, there's milk, all sorts of stuff. But in the glass of water, there's just one thing, and that's water. So what we're going to do is we're going to assign the term pure substance to something that contains only one substance in it. And we're going to differentiate substances based on their chemical formula. Now, if you can discern more than one thing in a substance, for example, there are 2 or more chemical formulas that you can write for the things in cake, then you designate it as a mixture. So we're going to take all matter that we interact with, and we're going to differentiate it as one of these 2 categories. Is it pure, or is it a mixture? And the question that we're going to ask is there only one substance in the matter? And that's going to designate which direction we go. All right, we're going to come back to this flowchart because we're going to add to it. We're going to split pure substances up into more categories and mixtures up into more categories so we can talk a little bit more about matter around us. On the screen, you can see 2 different types of matter, diamonds and table salt. These are the most important types of matter for most people. If you have diamonds, you're wealthy, and if you have salt, your food tastes good. What else can you ask for? Now, it turns out that diamonds are made of only one element. That element is carbon. We're going to define an element as anything that has only one atom in it. Sorry, one type of atom in it. If it had one atom in it, it would just be a single atom. Now, if you go to the periodic table, the elements are any of the substances in any of those boxes. There are up to 118 of these boxes on the periodic table. If your substance contains exactly one of those boxes in it, you have an element. For example, if you have a gold ring and the ring is entirely gold, you have an element. That is elemental gold. If you have a gold-plated ring, you do not have an element. You have a mixture. Because it would have gold on the surface where it's plated, and then some other element underneath, which would be like steel or tungsten or titanium or whatever. Now, because there's only one type of atom in the substance, applying energy or heat or something to it in order to break it down is ineffective. You cannot break down a single element into simpler substances through chemical means. If there were two or more elements present, you could split those elements apart and get individual elements based on what's in the mixture. For example, with table salt, we have sodium chloride present. So I could take this and I could split it into sodium and chlorine if I applied enough energy to it. So if I heated it, if I applied electricity, if I did stuff to this, I could turn it back into its constituent elements. And the reason that I can do that is because more than one element is present. If I have more than one element present, we call it a compound. Now, even though I have more than one type of element, it's still a pure substance. For example, pure water would contain only water molecules. However, water itself contains two elements, hydrogen and oxygen. So what we conclude is that water is a compound because it can be split into simpler substances. Those simpler substances are hydrogen and oxygen. Now, if you've never seen water broken down, it's actually kind of cool. So let me go get a YouTube video here. And I gotta find one just by looking at the pictures. Here's a good one. I've done this one before. So what I'm gonna put on the screen here is the way to chemically break down water. And you can actually do this at home, believe it or not, because all you need is a battery. Well, you need a battery and you also need thumbtacks. Alright, here's how this works. You see that there's thumbtacks that are pushed into this sort of like ketchup cup. And they're spaced apart so that when you put them on the terminals of a 9-volt battery, they line up and you have a contact. Now, the next thing that you need to do is you need to have some water with a little bit of salt in it. And when you do that, this happens. The salt is needed to close the circuit because a circuit requires a charge to be carried in a circle. But what will happen over time is that the water molecules will come into contact with the electrode, and the water will have its bonds broken and changed into just hydrogen molecules and oxygen molecules. Now, which substance forms where depends on which side of the battery you're at. Interestingly enough, because one side needs electrons and the other side gives them up. Now, as you scroll up here, I'm going to hit pause here. If you know what the formula of water is, which side do you think is the hydrogen side, and which side do you think is the oxygen side? And can you see that there's roughly twice as much of one as there is of the other? So that's kind of cool. So we can see the chemical formula of hydrogen and oxygen decomposing from H2O just by visually looking at it. Oh, there's twice as much gas on one side. There must be twice as much of that element, because we've let it run for the same amount of time, right? All right. Now you can do this with any circuit, which is what I think the video is going to do. But we get the gist of it. So the takeaway here is that you can turn compounds into elements by doing chemistry. But both of these can be pure substances. If we're talking about mixtures, doing chemistry to a mixture oftentimes either results in just regular old chemistry, or you get bizarre results because mixtures have many, many things in them. We're going to split mixtures into two categories based on their usefulness to us in the laboratory. And those two categories are the following. Any mixture that I have has different types of matter in it. But if I were to pour out, I need a different color for this, different portions of the mixture, maybe like the bottom of the container here. If I take any of these samples that I have circled of this ketchup, what I would observe is that they are all identical in terms of their taste and texture. If they're all identical in terms of their observable properties, they must be all identical in terms of their chemical makeup as well. There's an equal amount of vinegar, there's an equal amount of sugar, there's an equal amount of tomato. I don't know why I put tomato last in ketchup, it's the main ingredient, but there's the same amount to the degree that our senses can perceive in each portion. If this state is true, where all of the portions are identical, what we call this is a homogeneous mixture. Another example of a homogeneous mixture would be like seltzer water or soda or whatever. If you open a fresh bottle of soda and then you pour all of this 2-liter soda bottle into like 16 glasses, there will be no discernible difference between the glasses you poured first and the glasses you poured last, because you just opened the bottle. The solution is homogeneous. It's the same throughout. Another example of a homogeneous mixture is air. If you breathe the air on your patio, and then you breathe the air outside your front door, it's all the same air, because it's all mixed equally within a local region. Obviously, like the air here in Seattle and Everett is very different than the air in, say, Southern California, where it's very smoggy. I know this because I lived there. So the atmosphere over the entirety of the atmosphere is heterogeneous, but locally it would be homogeneous. Now down at the bottom here, with my salad dressing, you can see that some of my salad dressing is settled. This portion at the top right here, and this portion at the bottom, these are not the same. The top is more oil, and the bottom is more of like the spices and the herbs and the good stuff, right? Not that the oil isn't good. Like, it's certainly tasty, but I want the herbs and the salt and the spices and stuff in my salad. That's what gives it the most flavor. If you stir the heck out of this, it tries to become homogeneous, but it quickly separates out. If you've ever bought a bottle of Italian salad dressing, you have seen this happen. When you pull it out of the fridge, there's this thick layer of oil on the top, and you have to shake it before you use it. If you have a solution where the portions are not identical at the current moment, then what we call it is a heterogeneous mixture. Now, there is sort of an in-between of these, like a homogeneous mixture can become a heterogeneous mixture depending on like how you are looking at it. For instance, blood should be pretty homogeneous in your body, right? Like otherwise, if parts of your bloodstream weren't homogeneous, that could be a problem. Like that would lead to clotting or things like that. But at the same time, if you allow blood to separate into plasma and platelets, you get two different layers, and then it would be heterogeneous, right? So the examples that I'm going to select for you will be very obviously in one category or another if you apply a little bit of thought to it. For example, if you have water with sand in it, imagine putting sand in water. If you were a kid that had any sort of childhood, you have put dirt or sand into water and noticed that hey, it doesn't dissolve, right? So you would get you get a heterogeneous mixture. If you eat cereal with milk, the cereal doesn't dissolve, and so not every bite will have the same amount of cereal in it. Or maybe like the first bites will have all the cereal, and then the last bites are just the milk at the bottom, which is all sugary and gross. Yeah, I said it. I don't like the sugary stuff at the end of the cereal. Ugh, it's too sweet. I know a lot of people love cereal, and that's perfectly fine. But as you get older, I think that you just don't. You start to not like sugar as much. I'll eat dessert, but like cereal, it's not for me anymore. There's our completed chart. I'm going to add some little just fun things here that we've mostly already discussed. So you can turn a compound into an element through chemistry. So if you do a chemical reaction, you can separate out the elements that make up a compound and isolate them. Now, another interesting thing that you can do is you can turn mixtures into pure substances using physical means. For example, if you have a solid that is not dissolved in a liquid, you could filter one from the other. If you have two different liquids, for example, ethanol and water, you could separate those by distillation, where the ethanol boils at a lower temperature than water does. So if you heat it up to like 70 Celsius, the ethanol will boil out, but the water won't. So you could separate these out by physical means. Something to note for all of these mixtures down here is that what we have talked about is from a chemical perspective. I'm sorry, no, I'm thinking of the next step. We're actually talking about this from a physical perspective. Because we're talking about the state of what it looks like, or how many phases are present in our mixtures. You could end up in some very strange edge cases where it becomes very weird to describe something as homogeneous versus heterogeneous. And so it's important to distinguish this for our purposes. For example, we're only going to be considering the physical perspective of solutions and not the chemical perspective. So it is possible for something to be chemically homogeneous. And I actually want to discuss this on this slide really quickly. If I could click on this. Just to differentiate, because you'll see this terminology come up. You may hear the term chemically homogeneous, which means that there is only one element or compound present, which would be, by definition, a pure substance. But what we're going to care about for our purposes in doing these questions are things that are physically homogeneous. So and this would include all mixtures, and this is because these mixtures, if they're homogeneous, then these mixtures will only have one visible state. For example, my ketchup has one visible state. You could just see the ketchup. Something that would have two visible states would be, for example, this would be my salad dressing. I have the oil state up on the top, and then I have the more dense spices and such state. And you can actually usually tell that there's some sort of layer between those two. So this would be heterogeneous. Now, where does the confusion come in here? Here is an example of a solution that I could ask you and the answer that I would want. So if I gave you just water, you should immediately go, oh, that's a compound, and end of story. If I gave you just ice, you should go, oh, that's a compound, end of story. But what if I gave you ice water? Then what do we write for our answer? Which of the four categories, we'll put them on the screen here, do we pick here for this? And the answer is, well, it still contains only water in there, so writing compound would be valid. Because chemically, this is a pure substance. This is chemically homogeneous. But interestingly, I could also call this a heterogeneous mixture. Because there are two phases present. There's the solid phase of water and the liquid phase of water. And so in these very rare edge cases, you can get instances where you have multiple of these categories that apply. For the purposes of this class, I'm only going to give you substances or solutions where only one of the four statements at the top of the screen you see applies. You're going to have to pick one of these four things: element, compound, homogeneous mixture, or heterogeneous mixture. Okay? So there are cases out there where it can be ambiguous and you can have multiple answers, but you're not going to see any on any test or assessment that I'm going to give you. The only reason that I'm showing you the ice water example is because if you have problems in the textbook, they start to inch towards this concept of, oh, well, now we're starting to broach the difference between chemically homogeneous and physically homogeneous. And so it's important to know that these are guidelines. They're not hard and fast rules where everything must be compartmentalized into one of these four categories. For our purposes, we're going to do that. But do realize that there are lines that kind of blur if you get down into the nitty gritty details. And that's going to be true for a lot of science and a lot of chemistry, unfortunately. There's not much that is just discrete, absolute truths. Here's some more visual examples. What we're going to do is I'm going to put these on the board here, and what I want you to do is categorize them as one of the four categories that I listed before: element, compound, homogeneous, or heterogeneous mixture. So for each of these substances listed, select one of those answers and apply it to each of the terms. Be careful. If you aren't sure about something, consider how it is created or made. And then my final bit of advice is if there is only one substance listed in parentheses, that's the only thing in it. And if I give you a formula, it's just to give you more information about it to help you differentiate, okay? For example, in nail polish remover, the only substance in that bottle of nail polish remover is this. So hopefully that helps you differentiate stuff, okay? So apply one of those 4 categories to each of these choices. Type your answer in the chat, and we'll go over the answers together before we go on our break. So I'll give you about 4 minutes to do this. So see you in a bit. This is what I have to deal with. Like, she does not stop making that noise, which is cute, but hard to focus. I'll give you 1 more minute and we'll go over the answers. All right, let's go over the answers here. So Red Bull, is Red Bull pure? Can you buy pure Red Bull? Well, if you look at the ingredients on the side of the can, you can see that there's more than one thing in there. So it must be some sort of mixture. And when you first open it, Red Bull is a homogeneous mixture. Maya, just because I start talking doesn't mean you get to start talking. I was petting her and she was quiet, and then I turned my attention to you guys, and she's like, "Oh no, you have to pay attention to me." All right. If nail polish remover contains only acetone, and here's its formula, then it's a pure substance, and because it has more than one type of atom in there, we call it a compound. Now, with poorly mixed gravel, there are multiple things in here, which makes it some sort of mixture. But if it's poorly mixed and the substances are of different sizes and consistencies, there's really no way to mix it such that you will have the same amount of salt, rock, and sand in every scoop, especially if you poorly mix it. Nitrogen gas is only nitrogen listed, so if you look at the periodic table, you can see that nitrogen is just a single element by itself. And so we would discuss, or we would write that. Now, some crazy person decided that their favorite pizza was to put it in a blender. Don't blend pizza. That's just cruel and unusual. Pizza wants to be enjoyed. It wants you to sink your teeth into it. Nobody said the correct answer for the pizza place, which was Zeke's Pizza. I'm calling you out. I don't blend my pizza. I'm a pizza purist. Now, to be fair, deep dish pizza is already blended for you. So, I've had deep dish pizza and I was surprised at how good it was. I thought I wouldn't like it. Like, that's way too much sauce. And yet, I don't know, maybe it's just pizza. Maybe all pizza is good pizza. No matter how you have it. Even in a smoothie cup form or whatever. But pizza is always homogeneous. Because one end of the pizza, the crust, is going to taste different than the end in the middle, which is the center that you start from usually. And not every bite is the same. Now, just for reference, the best pizza is Zeke's Pizza. So, if you have not eaten a Zeke's Pizza, do yourself a favor and get some. It's expensive. I'm not gonna deny that. It's pricey, but it's the best pizza I've ever had in Seattle, anyway. Do they fire it in a kiln? I mean, they definitely fire it in a kiln, but I don't know if they let you build your own pizza. You might be thinking of mod pizza. Mod pizza is actually also really good. I've eaten at Brooklyn Brothers once, and I was like, this is okay. It's not bad. But Zeke's Pizza, every time I go, no matter which pizza I get, I'm always amazed by it. Iron metal, there's only one element in there, so that's an element. Steel metal, however, has a bunch of different elements in it, and you might immediately think, oh, this is probably a compound. But how do you make steel? Well, you heat up iron and all the other things until they're liquid, mix them together, and if in the liquid state, they are a mixture. And if you mix it well enough, it becomes homogeneous. Well, regardless of whether it's a liquid or a solid, it's still that mixture. So steel is actually a homogeneous mixture. And the sneaky thing about this is, so steel is what's called an alloy. And an alloy is any mixture of metals. And whenever you have an alloy, the result is always homogeneous. Pagliacci is okay too. I equate Pagliacci as to like one step above like Domino's slash Papa Murphy's slash no, Papa Murphy's is kind of its own thing. Pizza Hut slash Domino's slash whatever. Papa John's, that's the one I was thinking of. Pagliacci is better than that, but it's not super great. Surprisingly good pizza, Costco pizza. For how much it costs, like remarkably good. Don't know. I feel weird saying that, but Costco pizza is one of the better pizzas out there. Okay, I definitely went over on time for the break, so I'm gonna put the timer up. We'll get the music up. We'll take our 10-minute break, and I will see you in a little bit. Alright, we're back. Yeah, this is from the very end of the game, actually. Alright, so I don't know how much further we will get today, because I went a little long, and now I only have like 35 minutes left, but we can definitely talk about chemical and physical properties. We can get that out of the way. We'll do all the math on, what days do we meet? Tuesday and Wednesday? It says on my screen here, hold on. Tuesday, Wednesdays as well. Yeah, so next Tuesday we'll start doing the math stuff. We'll just get all of the conceptual things out of the way. So on the screen are a bunch of things that you can do to matter. There is a limitless number of things that you can do to matter. You can burn it, melt it, heat it, bop it, twist it, turn it, whatever you want to do. Some of those actions that you take to matter will just change its shape or its appearance or whatever. But other actions that you can take will irreversibly change the nature of the matter at the molecular level. And so what we want to do is we want to differentiate between what changes the identity of matter and what doesn't change it. We're going to use the identity as its chemical formula. So if I have water, for example, H2O, and I boil it, now it's steam, still H2O. That's going to be different than if I do the electrolysis of water, where it's no longer H2O, it's now H2 and O2. So the first terms that we want to define are properties and changes. A property is any sort of trait that a matter has that distinguishes it from other matter. For example, salt is like savory, but sugar is sweet. You can tell the difference between sugar and salt by just tasting them. They look pretty similar if you're just looking at the individual crystals from far away. Like, if you look really close on our microscope, they're very different. But, like, to an untrained eye, the difference is a lot harder to determine. But tasting it is very straightforward. If you have two different liquids, if you have water and gasoline, one evaporates much more quickly than the other. That's a property of it. So these are all different traits that we can ascribe to things that make them unique in some fashion. Now, a change is going to be any action that we can take that changes the properties of the substances involved. So solid ice melting into liquid water, the changed property would be its state. So it was solid, but now it's liquid. And the trick to this is figuring out, okay, did that change in properties and identity end up changing its chemical formula? And if it did, we're going to call that chemistry. If it did not change its formula, we're going to call it physics. So, like, throwing a ball at a wall is physics, because doing that just causes the ball to bounce off of it while the wall remains where it is. You still have the ball in the wall. If I drop the ball in hydrochloric acid and the rubber dissolves and reacts, I don't have the ball anymore, and I also don't have the hydrochloric acid anymore. I have whatever the reaction product is, which is probably some sort of inorganic salt or something. So that's our rubric. We're going to look at the formula before and after we take some sort of action. If the formula changes, we've done chemistry. If the formula does not change, we've done physics. Now, what are the chemical formulas for things? You're going to pick up the chemical formulas for stuff as you go on. Some common ones are H2O for water and O2 for oxygen. I by no means expect you to know any chemical formulas off the top of your head other than the really basic ones like water, oxygen, nitrogen, etc. Like, I'm not going to ask you what the formula for citric acid is. Like, that's ridiculous. Later on in the quarter, though, once we finished the first bit of Unit 4, I am going to have you memorize some compounds, and you will be expected to be able to form compounds from names and the periodic table. When I say memorize, I mean that in air quotes, because, again, this is an online class, so you don't have to actually memorize anything, as long as you have really good notes. you need to have an organizational system in place that allows you to get that information quickly. We'll go with that. All right. On the screen, I have an example of an action. I'm allowing my water to melt. But as you can see, solid water and liquid water have the same formula. What that means is that if the formula is the same before and after, all we've done is physics. We're going to call this a physical process. And I'm also going to introduce a different type of way to determine this. How hard is it to do the reverse process? It turns out for many physical changes, the reverse is fairly easy. For instance, if I want to freeze my water back into a solid, I just throw it in the freezer. I lower its temperature. That's not difficult to do. Now, in some cases, this gets a little bit obscure. For example, on the next slide here, if I cut my paper into pieces, well, I have paper before and paper after, so we can easily tell that this is the same, so it must be a physical process, even though I don't know what these formulas are. Now, this is sort of an obtuse question. Is it easy to reverse this process? I mean, technically, no, it's not easy to rebind your paper, but you can do it. And functionally, yeah, I can totally just do that. I could tape the paper back together. Functionally, that's easy to do. And when I say functionally, I mean, hey, if I tape the paper together, will it behave like it was a whole piece of paper? And if you tape it well enough, yeah, it will. It won't be exactly the same, but it'll be really darn close. When you change the state of the matter, what causes the molecules to coalesce into a crystalline structure? So we're going to discuss that a little bit in Chapter 10. And when I say Chapter 10, what I really mean is we tack on part of Unit 10 to Chapter 4. The force that is involved there is called the Intermolecular Force. You can think of molecules as being like really tiny and weak magnets. But even if they're weak magnets, if they're moving really slowly because it's cold, they'll stick to each other. And so you can make a solid that way. Water is particularly good at that, which is why water is such a high boiling point, because you have to heat it so much to get it to force apart. Molecules do tend to stick to each other, not through bonding, through a different sort of force of attraction. And again, we'll talk about that when we finish Unit 4 and talk about that little bit of Unit 10 at the end. It's called Intermolecular Forces. So, for our physical versus chemical, if you don't know the formula, thinking about how easy it is to do the reverse process, it still kind of holds up here. Because you could just tape your paper together and it should be okay. Let's talk about a place where this is difficult to reverse. That would be this. How do you unburn paper? Well, whatever this is before and whatever this is after, these are very clearly different. When you burn paper, a gas is released, and that gas is CO2. And we know all about CO2 because of climate change and global warming and all the discussions that we've had about that, right? So by burning this ends up being a chemical process. And yeah, that's exactly what causes water to be more difficult to boil. Is it's due to hydrogen bonding. And again, we'll talk about that at the end of Unit 4. So we can look at the formula. Again, we don't know the formula for paper. We know paper's a hydrocarbon, so it's going to have C's and H's and O's in it. Ashes tend to be sooty. The sooty stuff is the carbon. CO2 is the gas that's released. You also release water vapor when you combust stuff. All sorts of stuff. But the real easy way to do this is to say, oh, okay, can I turn my ashes and stuff back into paper? And the answer is with great, great difficulty. So what you'd have to do is you'd have to take all of the carbon that you collected from the burned paper, plant it in the ground, grow it into a tree, capture the CO2 into the tree that was released when it was burned through and do photosynthesis, then take all of the tree's trunk and stuff and turn it into paper. That's very difficult. It requires a lot of different processes to do that. Reversing chemical reactions tends to be difficult. Not always, but in many cases, chemical reactions tend to go in one direction, and the other direction requires us to provide a lot of energy. So this is a good indication of whether something will be a physical process or a chemical process. 1, look at the formula. 2, look at how easy it is to reverse it. Physical processes tend to be easy to reverse. Chemical processes tend to be very difficult to reverse. I lost my cursor. Where is it? There it is. I didn't want the arrow. I wanted to clear the ink on the slide. So difficult is defined as how much energy is needed to do it. That's a good clarification. So if something is easy, it doesn't require much energy to do it. You can think of energy as equivalent to effort. So like in the paper example, getting tape is pretty easy. You just tape the back of it and put the two pieces together, and it'll be close enough. You could still write on the paper. You could still send it as a letter. You could still fold it in half. Like, it retains almost all of its properties. All right, so now what I want you to do... Oh, I mean, the last little closing thing that we have here is, since this is a chemistry course, we're going to care about chemistry. We're going to look at chemical changes all the time, and we're going to be writing them in sentences like this. So this is a chemical equation. We're going to talk briefly about chemical equations later on in the quarter. For the most part, you're going to be doing that in 162. Physical stuff is common enough that we encounter it, so it's worth mentioning here. So what I want you to do is, using these statements, what I want you to do is consider, is the substance that is listed at the as the subject of the sentence, is that undergoing a physical or chemical process? So in the first sentence, the statement, water is boiled to make delicious pasta, the subject we care about is water. I think the only one where the first word or first words are not the subject is right here. So piece of lumber. So just highlighting that. We're not looking at the change the woodworker themselves undergoes, but the lumber in that case. So tell me physical or chemical for each of those. And then what I want you to do is, once you've decided one over the other, I want you to pick the word or group of words that tells you why you picked physical or chemical. Okay? I'll give you 3 or 4 minutes to do that. We'll go over the answers in a second. All right, 1 or 2 more minutes. Once you know physical or chemical, type your answers in the chat. All right, let's go over the answers here. Find my pen, it rolled away. All right, so I'm going to highlight all of the words or the subjects in yellow here. So water, grape soda, Alka-Seltzer, sodium metal, gunpowder, air, and gasoline. And then I'm going to get a different color. And we're going to find the words that describe what happens here. So first we got water. Water's being boiled. Whenever you change the phase of something from solid, liquid to gas, all you're doing is changing its phase. So it's still water. It's just now in the gas form. So this is going to be physical. Now, yeah, if you observe the world with laser eyes, then yeah, it would be chemical observations. But we don't do that. If you have laser eyes, you should see your doctor. Or Professor X, I guess, would be a better person to see. Grape soda is observed to be purple in color. Now, if you observe something, all you're doing is looking at it. Looking at something doesn't change its properties in any way, unless, of course, you're Superman or Cyclops or something like we're discussing in the chat. Those would be chemical reactions. But for the rest of us, that would be a physical change or a physical process. All right. Now, the third one's actually a little bit tricky because you might think, oh, dissolved in water, that's probably the key here. But it turns out that you also need releasing a gas because dissolved in water is not enough. If you dissolve some things in water, you can get them back by boiling away the water. But other things you dissolve in water change irreversibly, and you get back something totally different. Now, the releasing a gas is probably the more important of those two parts because it's the more distinguishing. Water does not release a gas. Alka-Seltzer does not release a gas. Putting them together releases a gas. So they must be undergoing some sort of reaction. For sodium metal, it's just melting. Melting is the change from solid to liquid. We've already discussed that phase changes are physical because you still have sodium at the end. When you ignite something, you burn it, you catch it on fire. It is very difficult to turn... Oh, I'm going to sneeze. Hold on. Hopefully it didn't catch that. Sorry. I sneeze really loud. It's very difficult to turn spent gunpowder back into usable gunpowder. Otherwise, bullets would be a lot cheaper, I guess, or a lot more expensive because they're reusable. So this must be a chemical process. In fact, any ignition, whether it's fuel, gunpowder, rocket engines, etc., those are all chemical. Very hard to do the reverse reaction. With air being compressed into a scuba tank, compression is just changing its shape. So you're taking a gas that was in a large shape, and you're just reducing it down to a small shape. So my gas is in here. Now it's in this tinier space, but it's still air. So that's just physical. What does it mean to whittle something? It means to cut it into smaller and smaller pieces, or cut smaller and smaller pieces off of the main thing until what you have resembles a chipmunk or art or something like that. Because what else do you whittle lumber into other than small woodland creatures, right? Now it's still wood, even though it has a very different shape. Therefore, it would be a physical change. And then finally, again, ignition, combustion, anything that you do of that nature is a reaction with oxygen. That's always chemistry. All right, looks like most people identify most or all of those, so that's great. Any questions, let me know. All right. The last thing we want to talk about for properties of matter is these two terms here, extensive versus intensive. Now, if I gave you, like, let's split the class into two people. Everybody whose last name begins with A through M, and everyone whose last name begins with N through Z. Okay. For everyone who's A through M, I'm going to give you a gallon of water. And then everyone who's N through Z, I'm going to give you a cup of water because I ran out. That's obviously not fair, right? But let's assume that I was in the classroom and I did this, and I asked you, whose water had the higher volume? You would go, well, obviously it's this one, right? But then suppose I asked you, whose water has the higher boiling point? And then the answer would be, well, both of them have the same boiling point. They both boil at 100 degrees Celsius, right? So some properties of matter depend on how much you have, and those properties are called extensive properties. However, other properties do not care about how much matter there is present, and those are called intensive. So something like density. Density is an intensive property. If you have more mass, you have an equal proportion of volume that is added in there, and thus the ratio remains the same. So for extensive and intensive questions, what you're going to be given is a bunch of properties, and you're going to have to ask yourself, if I poured myself twice as much of this, would this trait that I'm examining change? And it turns out that there are not that many traits that do change. All right, so my summary will appear on the slides here. So extensive cares about how much matter is present, intensive does not. You can have more or less or any amount and the property remains the same. I'm going to skip over these examples. I'm going to go just straight to these guys because we talk about weight on this slide anyway. So what I want you to do is, looking through these, try and flag the ones that are intensive and try and flag the ones that are extensive. If you have more of it, will this property of it change? Be careful when, because we're looking at property. Flammability is the one that I'm concerned about. So think about it in terms of, is it more flammable if you have more of it? Okay. So answer these questions, and we'll go over the answers in just a second. One more minute, we'll go over the answers. All right, let's go over the answers because we're running out of time for today. So if I give you more volume, or if I give you more water, does the volume increase? And the answer is yeah, so that must be extensive. Volume is an extensive property. Now, for flammability, let's pick something that's flammable. So if I give you more gasoline, does it become more flammable? Well, gasoline is already as flammable as it is. It will still burn whether you have a lot of it or a little of it. So this would be intensive. Its flammability is not affected by how much there is there. Now, how big of an explosion you get is affected by that, but that would be how much energy is released, not how flammable it is. So be careful about that. We already did boiling point. We said that's intensive. Mass, if I give you more water, its mass would increase, so this would be extensive. And then the last one, state. If I give you more water, does something turn into a solid or a gas? And the answer is, well, no, that's dependent on temperature, right? So this would be intensive as well. All right. Some properties are going to be just stated as extensive or intensive, and so it's just important to know what these words mean when we use them later. When we come back next week, we're going to get started with calculations and significant figures and stuff like that. So you probably remember from 140 all the fun of sig figs. We're going to do that real quick. We're going to finish that all up on Tuesday. And then on Wednesday, we should finish the chapter with some calculations, and then we'll move on to Unit 2. I got to find the button. There's the button that I want. That is it for this week. Next week, I'm going to stop putting announcements up that just say lecture begins. So it'll be up to you to make sure to check the YouTube page at the appropriate time for the live stream. It'll always be about 5 minutes before class starts. If I'm running late, it might take a little bit, so you just hit refresh until it shows up. If you're in the class Discord, I might type messages in there that are along the lines of, oh, running late. Sorry, hang out for a bit. And if there's an emergency or something, I will definitely post an announcement. But just so I don't flood your inbox with, lecture begins, it's like, I know I have lecture. I don't really want to go. Because, some people don't go to lecture. That's fine. You could watch this later. Other than that, have a wonderful weekend, and I will see you in week 2 for the rest of Unit 1 and the start of Unit 2. Take care and have a good one.